We're going to start the next step in our analysis in a familiar place. We're going to start with our expression for the first law, written as the differential of internal energy is just the sum of the increments in heat and work, but we're now going to, as we have in the past, write our work as an expansion work or expansion compression work. But now we can recognize that by specifying this P and it being the P of the system, that in some sense we're actually saying that this is an increment of reversible work, which means that our heat here is going to be an increment of reversible heat. Now if I rewrite this and separate the reversible heat on one side, I can write this as du plus P dV. Now I'm going to make one further assumption, and that is that I have an ideal gas. And when I have an ideal gas, that means I can write this internal energy as CV dt. And it also means I can rewrite this pressure as RT over V dV. Now you notice I've changed this to a molar volume because I don't want to deal with how many moles of ideal gas we have. Okay, but I have an expression here now that is a perfectly adequate expression for an ideal gas of the heat change for a given process. But this is not an integrable, this is not an exact differential, so it's not an integrable expression. The CV here is implicitly a function of temperature. The temperature here is implicitly a function of volume. And in fact, I can use the ideal gas equation of state to write down what that is. So in other words, I can't actually integrate this yet directly. These still represent, if you will, path-dependent functions. But I can make them dependent, I can make them exact differentials using a very interesting technique. I'm going to add an integrating factor. Okay, an integrating factor is basically a function that you can multiply by a differential to turn it into an exact differential. And in this case, the integrating factor I'm going to use is 1 over the temperature. Now let's see what happens when I multiply through by 1 over the temperature. So in other words, I'm going to take dq reversible, divide it by the temperature, and now when I divide by the temperature on the right-hand side, I'm going to have CV dt over T, and the second term is going to be R dV over V. Now what I have here is a bunch of things here that all depend only on temperature. And the second term depends only on the molar volume. So in other words, both of these terms now represent exact differentials that I can integrate. And in fact, I could, write this out explicitly if I'm going from a point that corresponds to, say, molar volume 1, temperature 1, to a point that represents molar volume 2 and temperature 2. And it doesn't matter how I go between those. I can simply do this as an integration of T1 to T2 of CV dt over T, and an integration from volume 1 to volume 2, again molar volumes, of R dV over V. All right, so this is how my integration would look. Now, if I work all this out, and I might as well since I've gone this far, remember that we're going to treat the constant heat capacity at constant volume, CV, as though it were constant, although we don't have to, but we will. And R certainly is a constant. So these things can be brought outside the integral signs, which means that I basically have the integral of dx over x, which we've already learned is just log of x. So I can directly write down the result of this as CV log of T2 over T1 plus R log of V2 over V1. And again, what I've demonstrated here is that these things depend only on the initial and final states. So what that suggests is this thing that's on the left-hand side must be a state function. And in this case, we're going to define this state function. It's actually going to become a state function that we care about a lot. We're going to define this as a differential change in a state function S. So this is a definition now that I'm writing for you of dq reversible over temperature. And this is going to define a new function that we will call the entropy. All right, now one thing you might ask is, do I have to insist upon this being a reversible heat? The main purpose for insisting upon reversible heat is that it will ensure that temperature is well defined for this process. And what we find is, for this particular definition of an incremental change in entropy, we need to be able to define what the system temperature is. That means it must be at some kind of thermal equilibrium.